Whenever you compile a program, there are actually 4 steps. There's the preprocessor. Let me do this. Hang on. I'm going to step up my game here. Preprocessor. There is the compiler. There is the assembler. And there is the linker. And the order they occur in is top to bottom. So when you say G++ assignment 3.cpp, those 4 things are actually occurring. So what you're starting with is, let me see if I'm able to move these a little bit. What you're starting with is your CPP file. All right. So this is your .cpp file. It starts at the top. And what I want to talk about first is you go through the preprocessor, and as a result of going through the preprocessor, what you end up with is C++ code. Now that you may be asking, what's the difference? The difference is this is a discrete file here, and this is just a bunch of text. So I'm going to elaborate on this a fair amount. I just want to draw the first part of this picture. Okay, so when you type G++ myfile.cpp, the first thing is the preprocessor chews on it for a little bit, and it spits out C++ code, and it's that C++ code that goes to the compiler. So you may be saying, well, I wrote C++ code, so what exactly is the preprocessor doing? So let me start with that. The preprocessor handles anything that begins with a pound sign. Pound include, and if you looked carefully at the coding standards for the first project, it would have had a pound if endif, pound define, and a pound endif, said surrounding header files with that. I'll talk about that a little later. But the one we all know and love is pound include, right? Pound include IO stream. So that is something that the preprocessor actually pays attention to and interprets. So let me write lamb.cpp. Mary had a little lamb. Pound include lamb.h. And here's lamb.h. Let me see. So there's lamb.cpp on the bottom half. On the top half I have lamb.h. And in lamb.h I will say with fleece as white as snow. Okay. So what I want to do is I want to run this through the preprocessor. It's clearly not C++ code, so if I actually go further than this step and I try to go to the compiler, it's going to be complaining to us. So I just want to do this first step. Now it turns out that the G++ command has options. So you've seen we've used the -O option. There's actually a -E option, and what that option means is only run the preprocessor and do not do anything else. Okay, stop at the preprocessor. So if I do that option and I give it lamb.cpp, here we go. Now there are a bunch of what I'm going to do is I'm going to finesse the discussion and say just avert your eyes and ignore anything that begins with a pound. This information the preprocessor is providing for the compiler, the next step that it's assuming will happen. For our purposes, we can ignore it. Note that here is the Mary had a little lamb, and then what it did is it put a copy of lamb.h right there. So remember me early in the semester saying pound include means literally put a copy of the file right there? Okay, so that is what the preprocessor is doing. So if you ignore everything that begins with a pound, there are only two lines here. Mary had a little lamb with fleece as white as snow. So when I say that the compiler gets C++ code, what it does is it gets a big long stream. All of this stuff is fed into the compiler. So if you're wondering how many lines of code generally are going into your coming out of your preprocessor, so this is just a shell of a program, 1, 2, 3, 4, 5, 6 lines. I think I've alluded before that there are a lot of lines here. We can actually measure that. So I've called this code.cpp. It's just an empty shell of a program. If I say g++ minus e code.cpp, and what I'm going to do is I'm going to take all of those lines and I'm going to output them to another utility. I'm getting into the realm of things that would be interesting in a Linux class. It's beyond the scope of this class, so take it as just a little bit of a recipe. This is a program called word count, and the -L option means give me a count of the number of lines. So this will tell me how many lines the preprocessor is spitting out for this simple empty main program that pound includes IO stream.
Wow.
Okay, so what that tells you is that the IO stream file has in the neighborhood of 37,000 lines in it. What also, if you were to actually find IO stream on your computer system and open it up, you'd find near the top it has a bunch of pound include statements. And if you found those files, they would have pound include statements. So there are probably, I don't know, 3 to 8 files total that are being included, comprising this total. And that's what the preprocessor is doing, just kind of marching through all these files, looking for the things that begin with a pound and grabbing a copy of the file. Yes?
Does the preprocessor also deal with anything that you might be using as well, like using any libraries you might be using, such as streams, or just the streams first?
The preprocessor is ignoring anything that does not begin with a pound. Okay. So if I again look at my output here, that means that note that this line did not begin with a pound sign. Again, ignore all this stuff. This is information intended for the compiler. The preprocessor saw this line. It did not begin with a pound sign, so what the preprocessor does is it just blindly parrots out that line. So we end up with all of your code plus anything like a pound include then causes a copy of additional files to be put at that location. It's another thing to note, and I did this explicitly, is that the pound include didn't begin at the top of the file. So that's really by convention and not by edict. All right? So you can put those pound include statements anywhere. They're almost invariably not as useful if you put them in the middle of your file, so they almost always are found at the top of the file.
I did it with the prime number program to add the name that we're supposed to use. Copy the file over.
You could use a pound include. So I'm going to get to, let me make the statement now. Never, ever, ever, again, this is by, I don't want to say convention, I want to say by, you will get in trouble trying to get your code to work if you do this. Do not ever pound include a .cpp file. I guarantee you, if you pound include a .cpp file, you're doing it wrong. And you may get it to work for whatever you're currently doing, but you will run into horrendous problems down the road if you get used to doing that. And we'll eventually get into the whys of that. But as a general rule, if it has a .h or things like IOStream, which don't have any suffix on them, those are fine to include. Never include a source file. Never include a .cpp file. Okay. All right. So that takes us through this next step, or through this first step. The next step is the compiler. This is the thing that actually takes all of that human-readable prose that you've written, but you've written that prose in a very specific syntax. You've made sure that semicolons are in certain places and curly braces and parentheses, right? You're following all the rules of the language. If you follow all the rules of the language, then what the compiler does is the compiler does not generate machine-readable code. There's another step to the process, which is to spit out what is called assembly code. I'll show you what that looks like. We'll look at it at a couple points. The way to look at, now I need to go to a different example because lamb.cpp is clearly not C++ code. I think what I'm going to do is I'm going to do this in C. So all I'm doing is I'm just changing the header file to standard.io.h. This is just going to help me not have to wave my hands a little bit further down in the discussion. But what I'm doing, everything I talk about essentially works exactly the same way in C++. Okay. So what I want to do then is take this simple program here. In fact, let me go ahead and write a little bit of code. I want to create a function called say hi. Seems like I did something similar to that at one point. And the say hi function I just want to do, if you recall in the C world, I use this printf function. Okay. And then I'm going to call that function here. So I'll call the say hi function. So there's my very, very simple program. I want to do now the first step and the second step, and I want to stop after the second step. And there's an option to do that, and that option is the dash. I want to say S. I don't recall. I think it's lowercase s. Let's find out. Oops. Oh, also I need to use GCC since I'm using C code. Again, it all works. This option works just fine with C++ code. All right. Let's try the uppercase S. There. All right. So is uppercase S. So these are options you don't have to memorize. Really, the only time you're really going to use them is when you're following along with me. And once you get to really advanced coding stage, then you might use those, come back to those options. But don't worry about having to memorize them. I'm not going to test you on them. You're not going to be using them every day. I'm just trying to separate all these steps out to help you understand what they're doing. Okay. So the dash E does only the preprocessor. The dash S does the preprocessor and the compiler and does nothing after that. When you get out of the compiler, then what you generate is a .s file which is assembly code. And we can look at that. If I do an ls, you'll see that it actually produced a .s file right here. We can look at that. Oops. Yuck. You will, if you're a computer science major, an electrical engineering major, you will have a class where you learn some assembly language actually writing this stuff. So what is assembly language? Every organization that produces a computer chip, excuse me, a central processor, two big ones that come to mind are Intel and Motorola, okay, and there are others. They all have what are referred to as an assembly language for writing code directly for that chip, okay? And that you can tell, even though this looks like gibberish, you can at least tell that it is human readable, right? It's not a bunch of zeros and ones, because no human on the planet can write programs in nothing but zeros and ones. So this is like the closest you can get to the machine as a human as far as interacting at a code level. And so all this assembly language is very specific to the Intel chip I have on this computer in front of me. If I go to a different chip that's put out by Motorola, then these lines here will look different because the lines are going to be specific to that chip. They'll end up, in the context of what I'm doing, they'll end up saying hi there, but the way you do it is different on every single chip, the way the hardware works. Your cell phone, right, is going to have its own assembly language. You name it. Anything that's a computing device is going to have a chip with its own language for communicating with that chip. So what the assembler is the assembler takes assembly language and turns it into something that is readable by the machine. That's what produces the ones and zeros. So that goes into the assembler, and then the output is a .o, and I would call that an object file. This is the ones and zeros. So the final step, I want to jump back up here, but the final step is for the object file to go into the linker. And what it does, I'll talk in more detail about it, what it does, but at a general level I can say it makes that object code so that we can run it. This object file doesn't quite have enough information in it for us to run it. It needs to put in some bootstrapping stuff so we can type a.out at the command line and it knows how to start up properly. Basically some kind of preliminary setup stuff that's needed for the environment. And that's what produces our a.out. Now we get a little bit, it's a little bit of a misnomer, but we now can understand what the historical reason is for a.out. What that stands for is assembler output. And it's just by virtue of history has been that for 40 or 50 years, however long it's been. All right. So let me talk just a moment about the linker. And let's look at what the assembler is producing. Even though we can't read this, I can point out things that you'll understand. First, let me look at the C code. Again, I wrote a function called say hi, right? And then I'm actually calling that function on line 10 here. So I can look at all of this gibberish here and I can find where that function is. This right here is the beginning of the say hi function. And you can see the comforting word say hi. And down in main, I called say hi, yes? So if I just go down here a little bit, here's where main starts. And right here, I'm going to call the function called say hi. And it's this that then jumps up here, runs this code up here labeled say hi, and when it finishes, it comes back down here. If I copy and paste this several times, so I call the function over and over again, and I look at it again, the assembly that it generates, there it is, right? Every time that I copied and pasted, it's calling that function over and over again. Okay? So, if the source code for the function is in the exact same file as where the calls are, everything's beautiful and works perfect. But it doesn't always work that way. Sometimes what I do is I create a different, maybe I don't want say hi in the same file that I have this in. Maybe I want to put this in a totally different file. So I'm going to say lines 3 to 6, I'm going to write those out to a file called hi there.c, or how about, I'll give it the same name, say hi.c. Okay, so here is say hi.c. I can compile that. So I say gcc say hi.c, and I'm going to give it that -s option so we can see the assembly code. I need my, since here's my printf, I need to pound include standard io.h. Okay, so I'm going to compile that. If I look at the say hi.s now, we can see here is the source code for that function. It looks exactly the way it did in main, and by golly it should. But you'll note that nowhere in here is there here's, look at this. Remember me, perhaps you remember me sometime in the past saying, you know, printf's just a function that someone wrote at some point. It is a function that someone wrote at some point, and here's the call to it. Okay, so all this is part of that say hi function. And that's all that's in there. Now let me go back to my main. Oops. Ccode.c. All right. Now what I have is I have to put this. Does anyone remember what this is called? On line 2. It's either a function declaration or another word for it is a function prototype. And again, this is information for the compiler saying, hey, should I decide to use this function, this is what it looks like. I have to do that now because the compiler will complain if I don't tell it first. And also I have to do it because it is in a different file now. That is the reason why we have prototypes and function declaration / prototypes, is because we tend to split this stuff up into different files. And this is the way I then inform main, or at least lines 6 through 9, that I'm going to be using that function. So let me go ahead and compile gcc -s. So now I compile the ccode.c. Here are all the calls to say hi. Here, 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 and here. But if I search for that, that's the only place. What's missing from this file now? There's nothing up here at the top that has a source code to say hi, right? Okay, so let's go back to this picture. So what I have is I have the say hi.cpp, and I have that main, which I called C code. So what happens is it'll go through the preprocessor, the compiler, and that's what we're looking at. It's a .s file, so that we can do the third step, which is the assembler, and stop there. That'll create the .o. And I can do the preprocessor, the compiler, and the assembler, and that will create a .o. Now, what do you think the purpose of the linker is? To link them together, because I have in one file, what file am I in? In one file, I have all these calls, and in a totally different file,
Say hi declaration.
I've got where it needs to go to call that function. So the linker is going to take the calls that are here, and it's going to link them to where the source is. So if I call it 4 times, it's going to link them in 4 places. That's why they call it a linker, because it links things together. Okay. So what happens when you compile more than one file, if I say G++, did I say the option for just doing the first 3 for preprocessing, compiling, assembling to get the .o? This is the one option that you will use quite a bit. So it's going to be GCC or G++, doesn't matter which one. You do -c. That means do only the first 3 steps and do not link. So if I say GCC-C, say hi, and then I do it to, what is it called, ccode.c. On both of them, I now have a .o file. So this is the ones and zeros. There it is, all ones and zeros. Now it's starting to make more sense why this will not run by itself. Even though this is all ones and zeros, this can't possibly run by itself because it wants to call the say hi function, and there is no say hi function in this file. Here, this is useless because this has the code to say hi function, but it doesn't do anything. There's no main in there to start things off. So we need to combine say hi.o and ccode.o into a single a.out. So when we say G++, or in my case GCC, ccode.c and say hi.c, this is a new one, it creates this a.out, and it is a combination of this .o and this .o. So what it did is it started the preprocessor, it did the compiler, it assembled it into a .o, then it stopped, it completely died, and then it started up all over again with this file, and it did the preprocessor, it did the compiler, it did the assembler to get the .o, then it stopped, totally died, and then it called the linker and said, please link these two files together into an executable, and that's what created the a.out. So if you have a file with 1,000 CPP files, then it's going to run these three things 1,000 times for each of those files, and it's only going to run the linker once to take those 1,000 .os and put them together into one executable. And in fact, now that I have the .os, I can say gcc say hi.o and ccode.o, and it'll create the executable. What happens is GCC will look at it and will actually see that this is already a .o, this is already a .o, and it'll just skip these three steps for both of those, and it'll immediately jump to the linker. What happens, so if I, right now, if I say GCC say hi.c, this will not compile, right? Because it's missing main. So what, of these four things, which one is going to complain? Of these four, which one's going to complain? It'll compile just fine. It'll create that assembly code just fine. The linker is going to complain because what we're going to have here is it's not going to have a main, right? Let's try it. So this here, whenever we've compiled programs in the past, we've always assumed it's the compiler complaining. Really, you all are getting a lot of problems from the compiler, but occasionally you're making it through all three of these and it's the linker that's complaining. The dead giveaway is this right here. This is the name of the linker, LD. That's the linker. So this is the linker generating this error, and now it makes a little bit of sense. It's saying, hey, I do not anywhere see main. Okay? It goes with the other one as well. So let me clear that. What if I try to compile the main? So again, main calls say hi like 4 times, but the source code for say hi doesn't exist anywhere. The linker is going to complain about, hey, you're trying to call say hi, but I don't see it anywhere. And there you go. Undefined symbols. It does not see say hi. And oh, by the way, you referenced it from, or you tried to call it from main. That's what that error is telling us. Okay? So this is all very new, and you're still fumbling along trying to get to understand the syntax of the language. But as you get better, you will be head and shoulders above everyone else if you're able to decide whether this error is coming from the compiler or it's coming from the linker. Right? If it's coming from the linker, that means all of your code is syntactically correct. It's just not able to marry up the names. Let me show you a typical example of where mistakes can be made. If I do yeah, I don't know if I'm going to be able to pull this off. If I do, because the compiler is probably going to complain here. If I have a typo in there, and I'm not encouraging anything here, so don't go out and be delinquents. I'd have to put this in here. So I can't get the perfect example. Whoops. So I'm trying to compile both C code and say hi. And you're going, and so I compile both of these. And you say, well, I've got both of these here. Why is it complaining? And what you need to realize is that you've got a typo in your function. Okay, so it's compiling it just fine, but the linker can't find stay high. Why? Because you do not have a function called stay high. It's called say high. And now when I do it, correct the typo, then I get an executable successfully. All right, so what I'm going to give you the secret word here in a minute. What all this ties into then is the make files, because it's the make file that helps us with this. We write make files so that if we have 1,000 CPP files, we make sure the make file does these 3 on each of the CPP files, and then it creates an executable from all the .os using the linker at the end. That's what we would end up using the make file for. Okay. So with that, I will